Hello everyone. Here I welcome you all to the part 3 of this e-content on bifurcation types. So in this e-content I will be introducing the Pitchfork and Hopf type of bifurcation. So what is pitchfork bifurcation? It is the third type of bifurcation where a system undergoes transition from having one fixed point to three fixed points. So it occurs generically in dynamical systems that possess symmetry. Now remember, in the part 2 video we have seen two other bifurcations. They were saddle node and transcritical, and they involved only two fixed points. So here in the supercritical or in the pitchfork bifurcation, we are going to have a transition from one fixed point to three fixed points. So there is going to be a change in the number of fixed points. So there are two types, supercritical and subcritical. So what would be the best equation that describes this behavior? It should be a cubic equation because three roots we should have. So accordingly we have this equation, dx by dt is equal to rx minus x cube. So now check the roots. What will be the roots? X is equal to 0, x is equal to plus root r minus root r. Now in order to check how the behavior, the stability analysis behavior is going to be upon variation of r, what you would do? You would take the derivative, right? So at x is equal to 0, if you take the derivative, what happens? R minus 3x square. At x is equal to 0, we will end up with mere r. So if r is less than 0, we are going to have a stable fixed point. If r is greater than 0, we are going to have an unstable fixed point. Now think of the other root, plus root r. What will happen? Now the root itself is plus root r. So what will happen? For r less than 0 case, we will have a negative value inside the square root, ending up with imaginary values. So there will be no fixed points for plus root r in the case of r less than 0. In the same way, even in the case of x is equal to minus root r, again if you take r less than 0, inside the square root you will again end up with a negative value. So no fixed points for r less than 0 for the case of x star is equal to minus root r. Now what will be the x star is equal to plus root r in the case of r greater than 0. So then you check the derivative. It is going to be r minus 3x square. If you substitute plus root r there, it is going to be minus 2r. So we will end up with a stable fixed point there. The same way minus root r also, if you substitute, it is going to be r minus 3x square. So x is squared. So again minus will be squared. Again you will end up with minus 2r. So it will result in a stable fixed point again. So what did you have now? So let us analyze this behavior with the help of phase portraits and bifurcation diagram. Very clearly explained here. So at x star is equal to 0, what did we get? We got actually one stable and another unstable fixed point when r undergone a transition from less than 0 to greater than 0. So we have the stable fixed point denoted by yellow circle, and this is a unstable fixed point denoted by green circle, right? Now what happens at the other roots? X star is equal to plus root r and x star is equal to minus root r. Both of them didn't have any fixed points at r less than 0, so no fixed points here. But r greater than 0, both of them had stable fixed points denoted by yellow circles. So now see, the system has undergone a transition from having one fixed point to three fixed points. Beautiful, right? So this is also explained here in the bifurcation diagram. You can see one stable fixed point, it changed to an unstable fixed point along with the creation of two other stable fixed points. This is supercritical pitchfork bifurcation. Now what is subcritical bifurcation? So it is going to be explained with the help of the reverse form rx plus x cube. So there is going to be again two roots. What are they? X is equal to 0 or x is equal to plus r minus root of minus r. So from here itself we can very well see what happens. So at r is equal to, at x star is equal to 0, that stable point will be merely having the derivative value at r plus 3x square. So it is going to be what? R again. So if it is greater than 0, it is going to be unstable, and if it is less than 0, it is going to be stable. Right? Yes, at r less than 0, we are going to have a stable fixed point for x is equal to 0. Now think about the two other roots. X is equal to plus or minus root of minus r. Naturally, if r is having a greater than value, then we are not going to have a real value here. Instead, it would end up with imaginary. So at r greater than 0, the roots with x is equal to plus or minus root of minus r are not going to evolve into a fixed point there. So we will not get fixed points for r greater than 0. But for r less than 0, what will we get? The derivative would be r plus 3x square. Now it is going to be r less than 0. So minus of minus root, it would be positive. So if you square it, it is going to be r plus 3 into square root, the entire thing squared. So it is going to be 4r. So it is going to be everything greater than 0. So it will be a stable fixed point for both the roots. Now this often leads to sudden jumps or hysteresis, where the system must leap to a faraway stable state because no equilibrium exists. So this behavior is seen here. So for r less than 0, we are going to have 3 fixed points. For r greater than 0, we will not have the 3 fixed points, but we will have only 1 fixed point. Right, which is an unstable fixed point. Now that same is explained with the help of bifurcation diagram also. Now remember, whatever I am describing here, you can have it drawn as a tabular column, having it as x star equal to the root 1, x star is equal to the root 2. Then take the derivative value f prime, and then check whether it is greater than or less than 0. So only if you systematically do, then these fixed point analysis will be smoothly done. Now let us get into the very interesting, the last type of simple bifurcation called as the Hopf bifurcation. So it is named after the scientist Hopf, or it is also otherwise known as Poincare-Andronov-Hopf bifurcation. Okay, so it occurs in nonlinear dynamical systems where a fixed point will lose the stability, and as the parameter changes, it will result in the birth of a limit cycle. So what is limit cycle? A periodic oscillation will tend to start. Now it is a local bifurcation that marks the transition from a stable spiral equilibrium to a periodic oscillatory state. It is in fact a two-dimensional analog of the pitchfork bifurcation. So there are going to be again two types, supercritical as well as subcritical Hopf bifurcation. So let us get into the mathematical analysis. So the normal equation, the normal prototypical example for this equation is going to be a two-dimensional form. dz by dt is equal to z into lambda plus I b of mod z square. So here lambda is a real parameter, b is going to be a complex parameter like alpha plus I beta, where alpha is the Lyapunov coefficient, right? So how can we solve this equation, and how are we going to explain the bifurcation, that is this periodic oscillation, how it is going to start here, the limit cycle evolution, how it is going to happen? Let us see. So here we find that the system is going to show two different behaviors depending upon lambda, the critical parameter, control parameter. So now let us get into the mathematical description of this. So we are going to do simple mathematical manipulations to depict the behavior of Hopf bifurcation. So the equation is nothing but dz by dt is equal to z into lambda plus I plus alpha plus I beta into z square. Now you substitute for z as r e power I theta. So we are going to have two parameters here, r and theta, right? So as we substitute this into this differential equation, we will separate the real and imaginary parts, leading to two ordinary differential equations. dr by dt is equal to r into lambda plus alpha r square, d theta by dt is equal to 1 plus beta r square. So if we do a simple mathematical manipulation here, d by dt of 1 by r square is equal to minus 2 by r cube dr by dt, we would end up with a shifted exponential equation of the form d by dt of 1 by r square is equal to 2 by r square lambda plus alpha r square. So the standard solution will be r of t is equal to r naught root of lambda by alpha, lambda plus alpha r naught square exponential of minus 2 lambda t minus alpha r naught square. So if the first term in the denominator considered to be very small, what would we end up? R naught square root of lambda by minus alpha r naught square. R naught square root of lambda by minus alpha r naught square. So we should have what? Real value. So in order to have real value, we should have positive values inside the square root. So where can we have the positive values? We will have two choices. Either we can have lambda less than 0. So lambda less than 0 at alpha greater than 0. So what will we have? We will have lambda less than 0, that minus, and minus alpha r naught square, that minus will get cancelled. That will be one case. What will be the other case? Lambda taking positive values, but alpha, if it takes the negative value also, we may end up with a real value for r. So those two would be the cases for getting the fixed points. So the same thing is explained here. So the limit cycle is stable if the first Lyapunov coefficient is negative. So as I told you, we will have two cases. If lambda, if alpha less than 0, that is the Lyapunov coefficient. Alpha, if it is less than 0, then in the denominator we had less than 0. So we can have lambda greater than 0. That is the supercritical bifurcation. Now otherwise, we will have the subcritical when Lyapunov coefficient takes up the positive value. If alpha is negative, then there is a stable limit cycle for lambda greater than 0. If alpha is positive, there is an unstable limit cycle for lambda less than 0. So this is beautifully depicted in the next slide. So this is depicted here. Where are we going to have the limit cycles? For lambda greater than 0, for alpha less than 0, or lambda less than 0 for alpha greater than 0. So can you see this from the picture? So only in the cases of 1b and 2a we have this limit cycle. One is a stable one and another is an unstable one. So that is Hopf bifurcation, resulting in the limit cycles, oscillations are born here from stable or unstable fixed point. What happens? Oscillations are born, and that is what we call it as Hopf bifurcation. So dear all, we have come to the end of the e-content modules. So we have seen successfully 3 parts, and here comes the summary of the types of bifurcation which we have seen. So the first one is saddle node, where two equilibrium points, they merge and disappear when a parameter changes. So it represents the creation or annihilation of equilibria. And second one is the transcritical, where the exchange of stability happens. The equilibria, they intersect and swap the roles. In Pitchfork, a single equilibrium, it will split into multiple equilibria. Namely, what we saw there, one fixed point leading to three fixed points. So supercritical and subcritical branches appear. Now there is yet another very interesting case of bifurcation, which you call it as Hopf bifurcation, where a stable equilibrium becomes unstable and periodic oscillations, limit cycles appear. So it is important for explaining self-sustained oscillations in physical systems. So thank you one and all. Happy learning. Meet you in another e-content video. Thank you.